do this. I'm going to say you have $100. Good old Ben Franklin, right? Let's give you more. Let's give you $1,000. You want more? A million? You could. The thing is that just seems unrealistic to me. I mean, I can't imagine what it'd be like to have $1 million just put in the bank, right? But maybe I can imagine having $1,000. And so I take that $1,000 and I go to the bank and I say, oh, well, what kind of interest rate can I get? And let's say I'm fortunate enough to find an account that'll pay me 4%. All right? So your first exercise is this. How much money do you have at the end of 1 year if you leave it in the account? And how much money will you have at the end of 10 years if you leave it in the account? Ready? Go. Okay. Any takers? At the end of 1 year, how much do we have? So we have 4%. If I write APR, do you guys know what that means? How many have seen those initials before? Sure, on a commercial. 4% APR means annual percentage rate. Okay, so if you didn't know that, that's nice to know. An annual percentage rate of 4%. And so how much, let's say, after 1 year, we would have how much in the bank? How'd you get 1,040? Well, what's 4% of 1,000? 40, right? So after 1 year, I'd have 1,040. How about after 10 years, how much would I have? Sure, I'd have 1,400 because I'd have 10 times as much interest, you might say. Okay? And then how about after 30 years? Any idea? 3 times 400? Okay. And so I'm ending up with 2,200. Okay. 2,200. And again, the formula that you guys mentioned to me was I equals principal times rate times time. Okay? And I'm going to write another formula from the book now. Okay? A equals P plus I. Of course, P stands for what? Principal. Okay? So this should make sense to you. If this I call the principal, it's sometimes also called the present value, and I is the interest, then what we did was we added the present value plus the interest to get my future value. So in my example, what I did was, for example, for this one, I computed that, let's see, how did I get my 2,200? Well, I had my present value was 1,000, and how much interest did we get? How did we get 1,200? Well, we did 1,000 times 0.04, which was, that gave me 40 bucks, and then I multiplied by what? 30 years, right? Okay? So I want to write down what it is you really just did, because I think this is important to understand. You did A equals P plus PRT. That's what you did, right? The future value, the amount, A, I got by taking the present value, 1,000, and adding this. Okay? Adding what? Well, this is called simple interest. It's called simple interest because it's a simple formula. But unfortunately, it doesn't actually describe what happens. Not really. As we'll see in a moment. Go ahead, Matt. I want to write down one more thing for you. Notice you have a common factor here, right? What's the common factor? P. So I'm going to write A equals P times, and do you know what I'm going to put in there? 1 plus RT. if I write P times 1 plus RT, I just want to point out that is another way to compute simple interest. And this is what people in finance do the most often. They'll do it this way. The first thing they'll do is what's in parentheses. All right? So I have my calculator ready. And so I'm going to type 1 plus, and what am I going to type next? What's my R, my interest rate? We're going to write 0.04, because that's how you write 4%. And then how many years? Well, we went with 30, right? Does this make sense? Boom. 2.2 times your 1,000 gives me my 2,200, right? Somehow, 1 plus RT tells me what to multiply by. Well, if you understand that, that's a good first step towards understanding finance. Okay. So I mentioned that banks don't compute using simple interest. Instead, what happens is we're going to use compound interest. See, here's the deal. It's important to understand that we earn interest on our interest. That's important to understand. Guys remember how much money I earned the first year? $40, right? Well, the thing is that $40 has been sitting in my account for 29 years by the time this happens. I better have earned some interest on it. And then the interest that I earned on that, I should earn interest on again. Okay? And compound interest makes a difference. And so one of the things I asked you guys, I remember, and those of you that have a bank account, do you know how often it compounds? Can I see a show of hands of people that do? Do what? If I'm going to compute how much money I have at any particular time, I need to know how often do they give me interest so that I can see how much more interest I have. So let me do this. Let's suppose we are earning 4% interest compounded quarterly. Okay? Again, start with $1,000. And my question is, how much at the end of 1 year, let's say? Okay? So I'm going to try and figure this out using my formula for simple interest. It's just I'll have to use the formula for simple interest at different times here, okay? So what I'll do is I'll do this. I'll say, well, A1, that's the amount after the first quarter, is going to be, well, I know it's P plus RT, P times parentheses 1 plus RT. And so in my particular example, it's $1,000 times, I probably should have made those parentheses bigger, 1 plus, I'm going to put 0.04 times what T? Well, you know what I better put? How about 1/4? Does that make sense to people? Because we're trying to figure out how much after the first 3 months. They're not going to give me a full 4%. Matter of fact, if you work this out, what's a quarter of 0.04? 0.01. I actually did this for a reason. It makes the computation quite easy, okay? So what do we get? we get 1,000 times 1.01. I guess at the end of 1 quarter, right after 3 months, we have $1,010. Does that make sense to people? And actually, that shouldn't surprise you, because remember how much I have at the end of 4 quarters was 1,040, right? So I'm on my way there. Okay. But then what happens when I do A2 equals P times 1 plus RT? It's not really P anymore. What is it that I want to put there? I want to put A1 there. Does that make sense to people? In other words, how much money do we start with when we're going to compute the second quarter? We start with 1,000 what? 10 times, well, none of this changed, right? Times 1.01. It's still 1 plus 0.04 times a quarter. So I'm going to go ahead and type that in the calculator. 1,010 times 1.01. And now I'm up to a whopping, see, it made a difference. How much of a difference did it make? How much? No? A dime, right? 10 cents. I now have $1,020.10. Aren't we happy? Okay, we'll see if this is actually worth it, right? Let's see. So then A3 is going to be this 1,020.10 times what? Well, still times what? Sure, we're always going to multiply by 1.01 because it's always the 1 plus RT. That hasn't changed. So I guess all I have to do is take my calculator and write times 1.01. Enter. Ah. And so A3 is 1,030 and how many cents? Well, 30. I have a question. Do you care about that extra tenth of a cent? How many do? How many don't? I don't see a lot. That didn't add up. Let me ask you this. Does Exxon Oil Company care about extra tenths of cents? They do. Matter of fact, what's the gas price? Don't they always write like, 359.9? Why do they do that? Well, first of all, 360 sounds a lot worse than 359. And secondly, those extra 9/10 of a cent you might not care about, but when they're selling billions of gallons of gasoline, it makes a difference. So one question I have is, does this make a difference? And the answer is yes. Okay? Sometimes. Depends on what you're talking about. It's not going to affect us much here. I mean, we have to do A4 to finally finish up. And so what am I going to put in? Well, I'll put in A3 times 1 plus RT. And so it's going to be, well, this amount that I just had times what? 1.01 again. And so we finish with 1,040. And should I call that 60 or 61? Yeah, I'll call it 60, I guess. All right. Are we glad we did compound interest? Really? You do all that work for an extra 60 cents. Seems like kind of a waste, right? Why did the banks do compound interest? Well, I guess for 1 year, it wouldn't be worth it. Bless you. But if we're talking 10 years, it may be worth it. And if we're talking 30 years, definitely worth it. And I'll explain that today too, I believe. Okay? So I need to just kind of explain one more time. You mentioned that the book has a formula for compound interest, right? And so you'll find that, I think, on the very first page of our section. Right here, let's see. This is page 469. No, that's the simple interest formula. Let's move down to page 470. Ah, there it is. The compound interest formula is different than the simple interest formula. Okay? And it says A equals P times 1 plus R over N to the NT. Well, I want to explain where that came from. See, look again at the work we just did. I guess the question is, could we have done this any quicker? Well, basically what I did was, to figure out the final value, A4, I started with 1,000, right? And then what did I do? I multiplied by what? Well, 1 plus RT. Remember that? And then I multiplied by what? Didn't I multiply by 1 plus RT again to get that? Do you guys follow that? Etc. Over and over again, we're multiplying by something, right? I don't want to write 1 plus RT. I'll remind you what we kept multiplying by was 1.01. Right? Okay. Well, the way that the compound interest formula works is this. A is going to be 1,000 times something raised to an exponent. And so the question is, what should that exponent be? Well, the exponent, they tell me, is n times t, where t is the number of years. And what's n? How often we compound. So the number of times we compound. Okay? And so, for example, if I want to use this formula to figure out how much money, say, after 30 years, well, what would we do? We would do 1,000 times 1.01 raised to what power? Well, what's n? The number of times we compound is 4. And what's t? Well, after 30 years, right, t is the number of years, so t is what? 30. Do you guys get that? So you're going to do 1,000 times 1.01 to the 120th, and that's what the bank is actually going to give you, not $2,200. Let's see how much the bank actually gives me. So let's see. Clear this out. 1,000 times 1.01 caret 30. Is it more than 2,200? Oh yeah, I did it wrong. Not 30 raised to 120. Sorry about that. So let's take the same thing and raise it to the 120 power. There it is. 3,300. Is that significantly more than 2,200? That's enough to make a difference. I mean, you've more than doubled your interest by doing compound interest. And that's why the banks do it. Okay? And of course, that's compounding quarterly. See, what happens is you get this exponential growth. And that's why compound interest is in our section. Because we have an exponent involved. So what I said was, let's go through this exercise. Now actually, there's a lot to do, okay? The first thing it tells me to do is find the amount in the account as a function of the term of the investment T in years, okay? All right, so problem 1 says, what are we doing? We're compounding what? Monthly. So let's see, actually, you guys can probably do this using our new formula. $500. It says invest it in an account, and it says that the interest is 0.75% compounded monthly. So the first thing they said is, well, find the amount in the account as a function of the term of the investment, T in years. See, if I go to use my formula now, I'm going to write A equals P times 1 plus R over N to the NT power. And I can start to fill things in, right? So my principal is 500. What I have here is 1 plus, what would you write here? I want to be careful here. That's right. This is less than 1%, right? So how do you write that? You write that as 0.0075. That's tiny. But then what else do I have to do? Divide by 12. And then I raise that to what power? Good, because n is 12. So we raise it to the 12t power. All right? And now I guess I'm ready. Let me use the calculator just to simplify that stuff in parentheses a little bit. So let me type in 1 plus 0.0075 divided by 12. There it is, 1.000625. All right, so my calculations are that we get 500 times 1.000625 to the 12t. You guys see that? And I don't know what t is. So what I can say is that I have written it as a function of time, a of t. That's what they wanted for part 1. They want to have you write an expression for the amount in the account. And by the way, what kind of function is this? It's a compound interest is where it came from, that's right. And it's, Delaney, it's an exponential function. Why do you say that's an exponential function? That's your base, right? That's being raised to the power of 12t. T is my input, and the input's in the exponent. You guys see that? That's why it's in this chapter. Because compound interest really comes from an exponential function. So now, what I can say is, I can compute how much will be in the account after 5 years, after 10 years, after 30 years, and after 35 years. That's what they want, right? And so this is very simple. You just need to put a 5, a 10, a 30, or a 35 in for t. So maybe I'll do a of 5 and a of 35 just to save time. Oh, by the way, probably the easiest way to do this, if you have a calculator, I go to the y equals screen, and I'll go ahead and type my function in here. 500 times 1.000625, and then what am I going to type next? No, you don't know? To the what? Oh, I see, because you want to do it to the 5th. No, what I'm going to do is I'm going to do this. I'm going to hit caret, parentheses, 60, no, not 60, sorry, 12x. Okay? I'm going to go ahead and type that in the y equals screen. And then you know what I'm going to do is I'm going to graph it. By the way, if I just press graph right now, I won't see anything. You know why? The window is way off. Here, let's suppose I were going to graph this by hand. Okay? if I were going to graph this by hand, do you know what the intercept would be here? This, of course, would represent when t equals 0. Do you know what a of 0 is? Well, a of 0 would be 500 times who cares to the 0 power. And why do I say who cares? Because anything to the 0 power is what? 1. That's why the exponential functions we've been graphing most of the time went through 0, 1. But our exponential function is going to go through 0 what? 500. Okay? So I need to change my window. So I'm going to put my calculator screen back here. I'm going to press the window button. And so, well, I haven't talked about x's yet. But let me talk about that now. I guess the smallest x value I need is, say, 0. And the largest x value I want, well, they want me to go up to 35, right? And why don't I put a mark every 5 so I can keep track? So x scale is going to be 5. And now y min, well, I guess I'll put 0. Y max, I don't know if you guys have any idea. Do you have any idea how much this is going to grow? You start with 500 bucks. I don't know. How about I put 5,000 and go from there? See what happens. I don't think it's going to grow nearly that much. Y scale, I'm going to put, how about every 500, I'll put a mark, and that way I'll be able to see what happens. So I'll press graph. Oh yeah, look at that. Is it growing? Well, relative to 5,000, it's growing, but not very much, right? Why don't I change my window then? Did it get above 1,000? I don't think it got above 1,000. Let me do this. Let me go to the window and make my y max equal to 1,000. I'll keep y scale at 500, and I'll press graph. So you could see that it did start at 0, 500, and now here you could see it's growing, but it's pretty slow growth. You guys see that? Actually, I should have known it'd be slow growth because the number that is my base is pretty close to 1, right? Actually, if it equaled 1, you wouldn't have any growth, right? You'd always have 500. Whereas the first example I did with you guys, when we had 4%, that's a lot. That's a lot of growth. Okay, but this is a slow growth. So my graph looks something again. It's growing, but slowly. It's slow exponential growth. Okay, so if I want a of 5, I can calculate what I get when I put in the value 5. So what's this mean? Now it says a of 5 is $519, right? Approximately, I'll just do dollars. Or I can hit second, calculate a value of 35. All right. So how do you interpret these statements? What would you say? How do you interpret what this says here? How much money? Yep. Right. After 35 years, we have 650 bucks. Okay? So far, so good. So it says, how long until my investment doubles? Well, how much money do we want in the account for that to happen? Okay? We want A of t to equal 1,000. So what I do is I take that equation, and where it used to say A of t, I'm going to write 1,000. And so let's see, what would it look like? It would look like this. 1,000 equals 500 times 1.000625 to the 12t. And you know what? This looks like an equation from section 3. Because what I want to do now is, if I want to know how long, you know what I have to do? I have to solve for what variable? For t. So what's the first step? Well, the first step always is to isolate the exponential function. Do you know what I have to do to this equation to both sides to get the exponential piece by itself? Right, we want to divide both sides by 500. And so I get 2 equals 1.000625 to the 12t. And then what's the next step? You got the exponential function by itself. How do you undo exponential functions? Take the log. That's right. So we're going to take the log of both sides. Do you guys like regular log or natural log? Regular log? All right, fine. When I say regular log, what's the base? Base 10? Okay. It really doesn't matter. You could do it either way. Log of 2 equals the log of 1.000625 to the 12t. And you might say, well, why did I do that? What good did that do? You could move the 12t out front. That's the most powerful of the log laws, is that 12t can come out front. So I have 12t times the log of 1.000625 is equal to the log of 2. Okay? And so let's see. 12t is equal to, well, how about this? The log of 2 divided by the log of 1.000625, whatever that is. And so for my final answer, I guess I get t is equal to 1/12 the log of 2 divided by the log of 1.000625. And so now I just have to be careful about typing that into a calculator. So maybe I'll do it this way. I'll type in log of 2, and I'll divide by log of 1.000625. So there's that answer, and then I have to do what? Divide that by? Divide that by what? 12. Okay. Ouch. T is going to equal 92.45 years. Don't put your money in that bank account, right? It's going to take 92 years for your investment to double. But that's because that's an extremely low interest rate. Okay? 4%, remember how long it took? It took less than 30 years for my investment. My investment tripled. Okay? So this gives you a little feel for interest rates you may not have had before. No, I don't really have time to do the average rate of change with you. I do want to show you this. He says, hey, I asked you, is quarterly better or monthly? All right. So he says, all right, guys, let's suppose you have $1 you're going to invest. For us, it was $1,000, right? And he says, how much money is in the account later? That's a typo, guys. Hold on. He said 100% interest. So that's kind of weird. You'd never get 100% interest. He'd double his money in 1 year. But notice the difference here between 4 years and 12 years. You guys see that? I'm sorry. Compounding 4 times a year or compounding 12 times a year, quarterly and monthly. Do you make more compounding monthly? Yeah, you do, right? And then in the next one, he said 360. That'd be like compounding daily, right? Compounding daily. Would you make more compounding daily than you did compounding monthly? You would. So what if someone said, let's compound every second? Well, someone could say that, right? Would you make more? Well, the answer is yes, but the answer is also not very much more. So here he shows you if you compounded 100,000 times a year, not much happens. And that's because you could show in a calculus class, for instance, or in a business class later with some calculus, that if you compound more and more and more, or let's suppose you could compound every instant, all you'd be doing is changing your base from 1 plus 1 to some exponent. You'd be turning it into 2.71 approximately. In other words, you'd be turning it into the number e, which we talked about in this class, right? E. So that's where, if you want to do this last section, you just use this formula, p e to the rt, and do the same stuff. This problem with you guys. So we're talking about what I'm going to call doubling time of an investment. So you take whatever amount you want, $100, $1,000, or whatever, and you're going to use the formula. And so I said continuous compound interest, and I said 3%. So if we say continuous compound interest, you know what your formula is. Your formula is A equals PERT, P-E to the R-T. Okay? And now, the fact that I have 3%, what can I do? What do I do with the 3%? Where does that go? In the R, right? So we're going to rewrite this as e to the 0.03t. And now, whatever amount you picked, that goes in for p. I'm just going to write p here. I don't know. Some of you picked 100, some of you picked 1,000. Okay? And then, what goes in for a? That's right. It's 2 times whatever you started with, right? Because we're trying to get it to double. It may be 200, it may be 2,000. If Delaney starts with 500, you want to put 1,000 here where the A was, right? But I'm going to put 2p here. And if I solve it this way, you guys are going to learn something. Because think about what variable am I trying to solve for? T, the time, okay? And of course, what I have to do, remember, step 1 for solving an equation like this is I want to isolate the exponential function. So how do I do that for this problem? That's right. I need to divide by p. Well, if I divide by p on both sides, it cancels. And so what do I get? Well, now I have 2 equals e to the 0.03t. All right? So what's my next step now? Trying to get the t. That's right. We're going to take the log of both sides. Why'd you say natural log? Right. So Augusto says, let's take ln of both sides. That'll cancel out the e. Right? These are inverse functions. So I think we're really starting to get the hang of the idea of these equations. Natural log undoes an exponential. Exponential undoes a natural log. So let's see what we get now. We get natural log of 2 is equal to, well, I guess it would just be 0.03t. Okay? And so t is going to be the natural log of 2 divided by 0.03. And here's where I could really use a calculator to help. So I'm going to go ahead and type that in. Let's see now. Natural log of 2, close parentheses, divided by 0.03. So there's my answer, right? T equals 23.1. So what is that? How do you answer the question now? The question was, how long does it take to double 23.1 what? That has to be years. Why does that have to be years? Yeah, why is it always in years? Well, I'll tell you why. I don't know if I've said this. I think I did once. When we give you the 3% here, that's an APR, which stands for what? Annual. So if it's an annual percentage rate, that's why we're working in years. Okay? But there's something key that we learn from this problem, and that's this. Does it matter how much money you start with when you're trying to figure out how long till it doubles? Doesn't matter, right? Because you're going to divide out by it anyways. And that's a key idea. Okay? Now, this ties into other applications. Like one of the ones that I assigned some homework problems for, and I didn't know if you'd get anywhere on them yet until we talked about it in class. It's one of the reasons I wanted an extra day today. There's some problems from the realm of science. We're talking about half-life. And I mentioned these, I think, Thursday last week. But the reason that doubling time doesn't depend on p is because of the equation, right? Because you put the 2p in for the a. And so this is a situation where compound interest is proportional to the amount in the account. And that's why, well, let's just say I could do a little calculus if I wanted, and I could show you that because of this fact, the fact that compound interest is proportional to the amount in the account, that leads to this equation. A equals an exponential equation. Okay? Now, we started to talk about this idea called half-life last time. Okay? So, what is half-life? Well, half-life is kind of like doubling time. But we're not talking about money anymore. We're talking about some element or some isotope. You know, something from the chemistry class. A substance on the earth that's radioactive, right? So the idea is that radioactive substances decay at a rate proportional to the amount of substance. I'm not sure you guys know what that means. Do you know what I mean by this? Proportional to the amount? Proportional to the amount? Let's see if we understand it from compound interest. Then I can try and explain the other way. Right? You earn more interest if you have more money in the account, right? You won't earn as much interest if you don't have as much money in the account. And that's why the picture of compound interest is exponential growth. Okay? Well, the reason half-life works, okay, is because radioactive decay is also proportional to the amount of substance you have. And so, even if I can't explain the mathematics here in this class, I can do this. I can show you a picture. And that is called exponential decay. Exponential decay. All right? So we're going to see exactly what is meant by exponential decay here in a minute. Right? I'm going to do a half-life problem, okay? I'm going to write down the following equation. A of t equals, do you know how to read that? A with the little zero? A sub zero, I'd sometimes say. Go ahead, Emily, you're going to say? It's called the initial amount, okay? Sometimes you'll read this as A initial or A naught from the German for zero, okay? But A initial, this is how much you start with, okay? How much you start with. And so it says E to the kt. All right? That's the equation. Actually, that equation looks just like the compound interest equation I just had. It's just that instead I had A and P and I had an R where the K is. Right? But it's the same equation, it's just different letters. Okay, and so this is the equation we're going to be using for these half-life problems. It's the same equation, just different letters. The only reason I'm using different letters, this is what the scientists use. The only reason I used R for the other time, that's what the finance people use. But it's all the same mathematics. Because, again, the amount of growth or decay is proportional to the amount of substance you have. The substance could be money. Here the substance is cobalt-60. If you don't know what that is, don't worry, I don't either. All right? All I know is it's radioactive, and I know the half-life. Now, what does that mean? Well, it's like this. They told me the initial amount is 50 grams, right? So where does that go in my equation? A initial, right? So where it says A initial, we're going to write down 50. E to the K. Now, T equals A of T. But this isn't helpful yet because I don't know K, right? I want to find K, so I will use the half-life. How do I do this? Well, what's that mean, half-life? It means the time I'm going to put in for T is going to be what? That's right. So it'll be K times 5.27 equals, now do you know what we're going to put in for A of T? 25. How come? That's half of 50. Right? If they tell me the half-life, I can put half of that here. Right? By the way, what if the initial amount had been 5,000 grams. Well, you'd have a slightly different equation. What would your equation be? 5,000 e to the k times 5.27. Well, what would you get over here then? 2,500, right? You guys see this? It kind of depends what they give you as an initial amount. Or more than that, it depends on what you pick for an initial amount. Because I'm telling you it's not going to matter. Because what's going to be the very first step I'm going to do if I want to solve for k? We're going to divide, right? So if I'm here, what am I going to divide both sides by? 50. And if I'm here, what am I going to divide both sides by? 5,000. And I don't care which way you do it. In either case, the new equation is going to say 1/2 equals e to the k times 5.27. Does this make sense? I mean, you get the same thing if you do it that way. Either way. All right, now what? What do I do next? Take the natural log of both sides. So we write down natural log of 1/2 is equal to 5.27 times k. And so I guess k is going to equal, well, 1 over 5.27 times the natural log of 1/2. And so I should work out a better value for k. I'll do, let's see, the natural log of 0.5, that's the natural log of 1/2, negative 0.69. By the way, do you see that negative sign? How did you know, why should I know that that's going to be negative? Less than 1, right? If you're taking the natural log of something less than 1, but you can only take the natural log of things greater than what? 0. So between 0 and 1, you get a negative. At 1, we get 0. And greater than 1, we get something positive. So that's good to know. Okay, and then what do I have to do? I want to divide by 5.27. And so I get negative 0.13 for k. All right. Now what's that mean? That means now I can write down my function. They want me to find a function that, oh, and it says keep the units of u and t as the same as the given data. And for k, they want me to round to 4 decimal places. So let's write negative 0.1315. Okay? Because that's what we had for the calculated value. All right, so my function now looks like this. Taking it from what's above, we can write a of t equals 50 e to the negative 0.1315 t. A of t equals that. That's an exponential function. Hey, by the way, you're putting in a negative number for your exponent. I'm just going to point out over here on the side that that's the same as, although people don't write it this way very often, a of t equals, what's the negative exponent mean? It means reciprocal, right? So this is 50 over e to the 0.1315 t. But people won't write that very often. Okay? Well, I'm just telling you it is. Anyways, I want to draw a picture of the graph. All right. What's a of 0 going to be? 50. That's right. A of 0 would be 50 times 1. Why is it times 1? Anything with a 0 power is 1. So it's 50, right? Now, because I have a negative exponent, okay, I want you to understand, well, what's going on here, okay? This is exponential decay. Because what happens is it's 1 over this guy, all right? So if I go ahead and sketch a graph, I'm going to have this kind of situation. Goes through 50, and then it gets smaller and smaller and smaller, but it's never going to get below 0. See, if you put in a number for t, you could see it up here, like 1,000. You'll be dividing by a big number, but you're still not ever going to get negative. So we still have 0 as an asymptote, it's just on the other side. Does that make sense to you guys? All right, so let's say you get some food and you want to know how old it is. You can look up the amount of cobalt that has decayed or that is left. And since we know how long it takes to decay, we can compute how old the food is if it's within a certain number of years. That's kind of the plan. So let's see what else they asked me to do. Determine how long it takes for 90% of the material to decay. So we know that half of the material would decay in 5.27 years. All right? 5.27 years is the half-life. So here's the last problem. We'll do that over here. How long for 90% of the material to decay? All right, let's see. And he gives a hint. He says, well, if 90% of the material decays, how much is left? How much is left? 10%. So here's the deal. My formula that I've been using is A of t equals 50 e to the negative 0.1315 t. Okay? But I want to see how long for 90% of the material to decay. So what I'm going to do is I'm going to substitute. I'm going to say, well, the amount I want, I started at 50, so I want 10% of 50. And so I'll put that in for the amounts. Okay? 10% of 50. And you could multiply that out if you wanted, you get 5. Go ahead, Matt. How'd I get 10%? Well, we want to know how long for 90% of the material to decay, and so the key is, this is the same as having 10% left. Right? So that's why 10%. Now, what's the next step? We're going to divide both sides by what? By 50. So let me go ahead and do that. I'll divide by 50 on both sides. Some 50s cancel. And so what I get is I get 10% equals e to the negative 0.1315 t. That's good? Now what? Take the natural log. Natural log of 10% is equal to negative 0.1315 t. And so t is going to equal the natural log of 0.1 divided by negative 0.1315. And So now I just need a calculator to punch in that final value, right? So I get a little glare. Let's see. Natural log of 0.1 divided by negative 0.1315. It's going to take 17 and a half years. All right? So if you look at the substance and you only have 10% of the original amount of cobalt left that you would expect in that substance, you're going to say, well, I know how old the food is. It's 17 and a half years old. Don't eat it. No, I mean, but maybe it'll help you date, you're fine. And that's kind of the way that scientists may use this. 17.5 years. So hopefully that helps you guys understand half-life a little bit. That sounds fair. Okay, so problem 28. All they tell me, and by the way, have you guys heard of this, carbon-14? When we say carbon dating, this is what's used, okay? The half-life, they tell me that the half-life is 5,730 years. What does that mean? What's that? No. Although, yes. What do I mean? I'm going to use that for T when I try to figure out what? The constant, the K. Here, let me write down the equation. The equation we've been writing down is A of T equals A initial e to the k t. Right? One of the problems is when Barr said they didn't give me enough information, like they didn't tell me something that I had in the other equations, and what was that? An initial amount. Well, we can do? We can make it up. We can make up whatever we want, and you know what? Just like, remember it didn't matter for the compound interest problem? It's not going to matter here. Let me show you what I mean. Favorite number, Abdel? I don't care. Favorite number. 5 is Abdel's favorite number, all right? So we're going to start with 5, all right? 5 what? I don't know. 5 kilograms of carbon-14? Probably not. 5 moles of carbon-14? How many have you taken chemistry? Moles? I remember that 6.02 times 10 to the 23rd. I don't know why I remember that number. But anyways, you put 5 here, all right? If I put 5 there, then what am I going to put here? 2.5, right? And I'm telling you it doesn't matter. If I put, like you said, n here, what am I going to put over here? 1/2 n. I don't care. E to the k times, and yeah, the half-life is going to be 5,730. And the reason I don't care what number you put in for n is because what's going to be the very first step? If you're trying to solve for k, what's going to be the very first step? Divide both sides by n. Right? So I get 1/2 e to the 5730k. Mitch, you with me? You're awake today, which is good. You know what to do next. So now we take the natural log. Natural log of 1/2 is 5730k. Hey, I said I wasn't going to do this for you. Well, there are 4 more parts. That's good. Okay, so then, well, I guess from here, we'll get it, right? We'll get what, eventually what's going to happen is we'll get what k is, and then you'll have the function. And then you have to use that function for parts B and C. And part D says, research radiocarbon dating and discuss why this model is oversimplified. That's kind of extra credit now, isn't it? Okay? Does that help? Go ahead and show it, huh? Or how many got that? Checkpoint quiz 5.2. They give me this function. F of x equals 3x over x plus 1. Part A says find the inverse. I'm going to do this real quick there, Barb, and then I'll do B. So find the inverse. Well, what's the steps? First I want to write y equals 3x over x plus 1. And then what do I want to do next? We want to switch. So we're going to switch the x and the y. So I'll write x equals 3y over y plus 1. Okay? And so now, solve for y to find the inverse. And by the way, this here, again, I switch x and y. Because you're switching input and output. That's what an inverse is. All right, so I want to solve for y. So let's see what I get. Oh, how do you solve for y with an ugly equation like this? Actually, I'm going to pause and let you talk to someone next to you about that for 30 seconds. You know, I'm going to do it anyway, though. I'm going to multiply both sides by y plus 1 and just see what happens here. So now what am I going to do? You want to divide by 3? I guess I'd have this y by itself then. But the problem is that there's also a y over here. This one's a little tricky. Here, watch this step. Let's distribute the x. How come? I don't know, just because. It's my instincts. xy plus x equals 3y. Next step, let's subtract the xy. Why did I do that? That's right. If I get all the y's on one side, everything that has a y, and if I get everything else over here, there's a really nice trick we can do, and that's to factor. That's right. We factor out what? Y times what? 3 minus x. Okay? And now if I solve, I get that y equals x divided by what? 3 minus x. So here's my inverse. My inverse function is x over 3 minus x. That's the inverse function. Now, that's not what Barb asked about. Barb asked about composition. What's supposed to happen is that, so part B says, check your answer using function composition. And so what that means is, well, if I do f composed with f inverse of x, what am I supposed to get? X. Also, f inverse composed with f of x, I'm supposed to get x. That's what's supposed to happen. So I think I have just enough time to do one of them. Which one, Barb? The first one? Okay. So this means f of f inverse of x, right? And that means, well, f of, here's f inverse, right? F of x over 3 minus minus x. That's what f inverse is. How the heck am I going to do that? Well, okay, I remember that f of x from above was 3x over x plus 1. So when I say do f of f inverse, what that means is everywhere there used to be an x, I'm going to write what? X over 3 minus x. Now this is a little crazy. Plus 1. So I have to simplify this? Now here's my trick. I'm going to multiply by 3 minus x over 3 minus x, top and bottom. On the top, the 3 minus x's cancel. On the bottom, you have to distribute. When you distribute on the bottom, you get x, because the 3 minus x's cancel, plus 3 minus x. And up in the numerator, I get 3x. So I just get 3x over 3. There's half of it. You guys can try the other half on your own.